Just like the normal form of the equation of a straight line in Cartesian coordinate geometry, even in three-dimensional geometry we have the normal form of the equation of a plane. Remember, the three-dimensional equivalent of a straight line in Cartesian coordinate geometry is the plane and not the line in three-dimensional geometry. So therefore, all of the equations which we find for a straight line in Cartesian coordinate geometry have something analogous to them in the equation of a plane in 3D geometry, with the addition, of course, of the z part, where you have only x and y part in Cartesian coordinate geometry for straight line. As you must have noticed, most of the equations that you have studied till now, equation of a plane and intercept form and equation of a plane and vector form and all that, they resemble the equation of a straight line very much with the z term added to them. So therefore, here also in the normal form we have the normal form of the equation of a plane, which is given by r bar dot n cap is equal to d. Now of course this is a vector form because it's three-dimensional coordinate geometry, so you can express many of the lines and the points using vectors. So the vector equation of a plane which is normal to the vector n hat and at a distance of d from the origin is r bar dot n hat is equal to d. Now how does this happen? Let's take a look at a diagram representing this situation. O is the origin here. From the origin, a perpendicular is drawn to the plane. So this represents the shortest distance between the point, that is the origin, and the plane. So that is represented by the vector NO bar. We have another random point P whose coordinates will be general x I cap plus y j cap plus z k cap. It's represented by the vector r bar. So ON is perpendicular to the plane. So therefore, when we take dot product of r bar and n cap, what do we get? We get the shortest distance between the origin as well as the plane, and so therefore this dot product represents the distance d of the origin from the plane. So therefore this gives us the equation of the plane in simple terms. Of course, for this we need to know the unit vector n cap in order to be able to write down the equation like this. So therefore, let's look at a simple example demonstrating this. We'll do this later on, except Cartesian form of the equation of the normal form of plane. If L, M and N are direction cosines of the normal to a given plane, which is at a distance p from the origin, then the equation of the plane is Lx plus My plus Nz is equal to p.